Without further ado, it is my honor to introduce our morning keynote speaker, Marcia McNutt. Early in her career, Marcia was a professor in geophysics in our IPS department here at MIT. Since then, she continued her brilliant career as a faculty at Stanford University, as president of the Monterey Bay Aquarium Research Institute, as the 15th director of the US Geological Survey. Marcia is currently the editor-in-chief of the journal Science and has been nominated as the next president of the National Academy of Sciences, where she vowed to make climate a cornerstone focus. Marcia.
All right. Well, thank you very much. It's clearly an honor to be your opening keynote here today, to be able to speak on something that is a passion of mine and a topic that, as you heard, is something that I hope to be spending a lot of time on in the very near future. As you all know, climate is something that is on all of our minds recently, not only with the record heat wave that we've had in the past decade, but with the snowstorm that we had this past weekend. And so I wanted to start with this first question. Climate science, is it settled or isn't it? And I think we can talk about this both yes it is and no it isn't, depending on the kind of question you want to ask. If the question is the climate changing due to human action, we can make the argument that yes, we know enough about that question to say that we should be taking action to limit greenhouse gas emissions. And that was the basic reason why in the Paris talks, nations came together to limit greenhouse gases. So it is settled in that respect. But from a scientific standpoint, there are a lot of questions that do remain to be answered. For example, exactly how fast do we expect sea level to rise? How will weather events, particularly extreme ones, respond to climate change? How will ecosystems respond to climate change? And how will humans be impacted? Because in the end, it's all about us. Many of us in the audience here are geoscientists, and we know the climate's been changing for 4 billion years before we started changing climate. The Earth will go on, but will it go on in a manner that is amenable to us? So if we want to answer questions like, how quickly does Logan Airport or San Francisco Airport need to be moved inland? That's a question that we need more science to answer. And all we have to do is look at what's happened to the Jersey Shore with Hurricane Sandy or with this most recent snowstorm and say, if we don't want that to be Logan or we don't want that to be SFO, we need better science. So what I'd like to do now is just take you on a little journey of a potpourri of some recent papers that have been published on the pages of Science magazine to show you that there are still many outstanding questions in science that need to be answered and are being investigated that are important to know if we want to understand what is our climate future and how is it impacting us. So this is one that got a lot of attention in the past couple months, and not all of it scientific necessarily. And this was a paper by Tom Carl and his colleagues at NOAA that asked the question, was there a warming hiatus? And what they did was they carefully looked back at ocean data on warming over the past few decades. And what they noted was that there was a small but very systematic offset in ocean temperatures between temperatures that were taken by buoys and temperatures that were taken by ships. And although the difference was small, it was systematic. And when integrated over the oceans, it was enough to eliminate the hiatus. And that's in that middle ocean panel, and you see the squares are the corrected data when you eliminate that offset, that systematic offset between the ships and the buoys, and the circles are the uncorrected data. And you can see the land, there was no need to do the correction, and there never was a hiatus, and it was only in the ocean because of that offset. Now, unfortunately, because of doing that correction, that only added fuel to congressional concern that scientists are manipulating data. And so this was an unfortunate case in which, by going back and doing a careful reanalysis of data, scientists only lended fuel to concerns by those who liked the hiatus, that scientists were changing the story in order to fit a preconceived opinion. This is another story from the pages of Science that I thought was incredibly interesting. And let me explain to you that the vertical axis on the left is an axis that shows over time the amount of ice loss. So as you go down the axis, that's more ice loss. And on the right, it's more sea level rise. So sea level is rising as you go down, and ice is being lost as you go down. And these are different models of how this Thwaites Glacier is going to lose ice. And what this basically shows is how little we know about how ice sheets are going to disintegrate. And this is very important for how quickly sea level is going to rise. And the red line at the top in each of these is basically a steady state model. And all the others are non-steady state models, where you can see the black line shows a very rapid disintegration of the ice sheet and a very rapid sea level rise over 50 to 100 years in the black lines. And what it depends on are things like the melting profile of the glacier, how much snow is falling on the glacier, and what the boundary conditions are at the edge of the ice sheet. Is it buttressed, or does the buttress fall away? And basically what we're seeing in these models is we could get rapid ice sheet collapse, or we could get slow melting of these glaciers. And right now, we don't know how quickly these ice sheets are going to collapse. So this is a very, very important problem in future climate to solve if we're going to know, do we have to rapidly move coastal dependent facilities inland, or can we slowly move them? And this is big dollars. If we abandon a facility and move it inland too soon, that's expensive. If we don't move it fast enough, then that's expensive. So this is a very important problem to solve. Here's another question. How will the ocean's ability to absorb CO2 evolve with climate change? The oceans can either help us by creating a positive, by absorbing more CO2 and helping to mitigate climate change, or it can stop absorbing CO2 and we can have runaway climate change. And previously there was concern that global warming slowed the uptake of atmospheric CO2 in the Southern Ocean in the 1990s. But here was a paper that was published in Science by Landshooter et al. That present newer data showing that the Southern Ocean carbon sink strengthened again over the past decade, since the 1990s, which illustrates the dynamic nature of the process and alleviated some of the anxiety about the earlier trend. And what it actually showed was that the Southern Ocean set up this dipole with warmer water in the Atlantic side and colder water in the Pacific side. Now, whether this will persist or not, we don't know, but it shows that this is not a steady state trend, but it's a very dynamic nature, something that is worth monitoring and paying attention to because the partial pressure of CO2 is changing. Here's another study on how changing climate affects ocean circulation. Rapid warming in the Arctic influences mid-latitude circulation by reducing the poleward temperature gradient, because the Arctic warms more, and so that latitudinal gradient changes. And this is a paper by Camus et al. That reports significant weakening of summer circulation and zonal winds, Rossby waves, and eddy kinetic energy. This weakening of zonal winds is explained by a reduction in this poleward temperature gradient, but monthly heat extremes are associated with this low eddy kinetic energy and fewer summer storms, and thus may have contributed to more persistent heat waves in the recent summers, particularly in Europe. So, and that's shown with this data that you get temperature anomalies because of the eddy kinetic energy. And then how climate affects drought is another problem. Net hydrologic effect is difficult to predict with climate change, and it's difficult to distinguish between droughts and background dryness itself. The background dryness depends on precipitation increases and also how fast water evaporates. And right now, we can't predict this net effect. We might get more rain, but we also get more evaporation. What's going to be the net effect? This is very important for the American West. This was a dramatic cover for Science about lightning effects. There are around 25 million lightning strikes per year. Romps et al. Constructed a model based on convective available potential energy and precipitation rates to explain the frequency of lightning strikes, and they predict that lightning strikes are going to increase by 12% for every degree of rise in global average temperature. And tornadoes, how are they going to respond? Brooks et al. Saw no clear trend in the annual number of tornadoes between 1954 and 2013, but they saw more clusters of tornadoes. So there are more days with multiple tornadoes. So why this clustering effect has occurred is not clear, but this is something that also needs more work in terms of understanding what storms are going to be like in the future. And finally, can individual events be attributed to climate change? This is something in terms of trying to help the public understand what's the future with climate change. Anthropogenic climate change is expected to increase the frequency of heat waves and other extreme events, but the same has not been established for individual events. Recent studies appear to identify the role of anthropogenic climate change in, among other events, the 2010 Russian heat wave, the 2013 Australian heat wave, and ongoing drought in California. And those seem to be individual events that are tied to climate change. And that's important when we try to communicate to the public what how climate change is affecting them personally. And then finally, how will oceans respond to acidification? This was one of the few positive stories that emerged from climate change, because these coccolithophores may actually benefit because their photosynthetic ability is strongly carbon limited. And this study showed that the abundance of coccolithophores in the North Atlantic actually increased by up to 20% or more in the past 50 years because of increased CO2. So in summary, ultimately, we care about anthropogenic climate change because of its impact on us, via sea level rise, extreme weather events, crop yields, and changes in ecosystem services. Better predictions of what to expect can, at best, prompt action to mitigate anthropogenic climate change and, at a minimum, guide more timely decisions on adaptation. And I think those should be the goals of what we want to do with our science. Prompt action and guide timely decisions on how we need to change to adapt to what's happening. So thanks very much, and I'm happy to take a question.
While we switch it, working now, yes. While we switch over, there's time for one quick question while Kurt sets up the next speaker. Thank you very much, Marcia. It was great.